So graph analytics has been around for a very long time, but given the increase of generative AI and the need for organizations to really get a good handle on the data that they're working with, graph has come up much more into the data ethos. So I think it's a fantastic topic to talk about. So again, I'm Andrew Madsen. I'm an evangelist at Dremio. And I'd love to connect with you on LinkedIn. That's where I get a ton of questions and love engaging with folks there. So please feel free to add me and send me some messages. On the side, I'm a professor of data science and data analytics at a bunch of different places, as well as active on LinkedIn and on YouTube. So just real quick regarding like what is Dremio, because I usually get that question sometime during my presentations. I'll talk about it right now and then we can get into graphs. So Dremio is a data lakehouse platform which helps you unify your analytics. It helps you run a SQL query through all your sources, so it can federate your queries and it can do total lakehouse management, multi-cloud, on-prem, or hybrid. Speaking of open source, we do offer a free copy of the Apache Iceberg, the definitive guide. Apache Iceberg's the technology which makes a lot of lakehouses possible. You can use Iceberg, Delta Lake, sometimes Hootie if you're highly transactional, but it's like $70 on Amazon, so I would recommend you just get a free copy. So you can use this QR code here to download a free copy of the Apache Iceberg definitive guide. It's around 400 pages and takes you from the fundamentals all the way through hands-on. All right, let's dive in. So I thought a lot about what can we talk about with graph analytics, because there's so much to talk about. It's such a really broad space and there's a lot of applications. And I finally decided on, okay, let's do a fundamentals and we can follow up later with some more in-depth on graph analytics, because it's such an interesting topic, so many use cases, and you can really dive really deep into each component of graph analytics. There's so many algorithms or techniques and math behind it. So we're going to go through an introduction to what it is, some of the common graph data modeling types and techniques, and really dive into some real world examples and the tools that you can use. I mean, there's thousands of tools, so we'll just cover some of the highlights and the open source tools, and then do a quick demo of what it may look like using only open source and Python in this example. So let's talk about like what is graph analytics, because it's really a powerful approach for analyzing connected data. And it's really transforming how organizations derive insights from complex relationships. And relationships is really key to graph analytics. And so graph analytics, it's like the science of analyzing connected data where relationships between entities are just as important as the entities themselves. So it's like looking at a social network and not just seeing individual people, but also understanding their friendships, their interactions, and their influence on each other. The field's built on a mathematical foundation of graph theory. If you've taken graph theory in school, you're fairly familiar with it, and you're like, oh no, here we go. Don't worry, we're not going to go deep in graph theory today, but that is the foundation of graph analytics. And it provides the tools and concepts for representing and analyzing those networks. And the primary focus of graph analytics is really to discover patterns, communities, paths, and hidden insights within connected data. So for example, imagine identifying groups of customers with similar purchasing behaviors, or finding the most influential people in a social network. And how do you visualize that? And how do you define what's influence? That's where graph analytics can come in and really distinguishes itself by being able to help answer those questions. So it's a little bit different from traditional analytics in a few key ways. One, I already mentioned the focus on relationships. So while traditional methods of analytics often focus on individual data points, graph analytics emphasizes the connections and the interactions between them. The second part is efficient transversal of complex networks. So the more complex the network gets, the better the advantage is of using graph analytics over other methods, in my opinion. So graph databases, particularly like Neo4j, are designed to efficiently navigate those relationships, which really makes it possible to analyze those vast networks with billions of connections. Think about like Facebook and the 2 something billion active users and all the relationships between them. And one thing I love about graph analytics is it's really a natural representation of real world connections. Sometimes in analytics, they really should be an example of the real world, but often we're just dealing with aggregate statistics, averages, median, min max, where graph analytics really is representing entities and our relationships. And it can be social networks, supply chains, financial transactions. It's really amazing. And I love diving deep into it. And I hope more people take this to get curious about developing their graph analytics skills, because it's really applicable to so many positions: data analysts, data scientists, AI engineers. All these people are interacting with graphs. And really, graph analytics can not just do direct relationships, but it can also do indirect relationships. So it allows us to find not just these direct connections, that's easier to visualize, but indirect relationships like friends of friends. And that also helps with fraud detection and some of these key use cases. So some of the key components, and this is super basic, this is fundamentals. I know there's other ways to build this, but in general, some of the key components of a graph, you've got the nodes, entities. These represent nouns. That's how I think about them. So it's entities in the network: people, products, locations. Nodes can have multiple labels depending on the graph. So it can provide context, categorization. So like a person could be labeled a customer and an employee and a manager. So they can store properties like key value pairs, holding information about the entity. So it could have name, age, address, depending on the complexity and density of your graph. And each node has a unique identifier to distinguish it within the graph. So it helps us navigate around it. Then we have edges, which represent the relationships, and they can be directional. There are also non-directional graphs. Typically, they are directional. And edges connect exactly two nodes, defining the relationship between them. They can be, as I said, directed or non-directed. And then you have labels, such as describing what the action is between the two nodes. In this case, purchases could be one. Filling in those labels, those properties, really helps explain what's going on, which is why I love the real world interaction that graph is really trying to model. And so this is where it can become complex within an organization, within financial data, purchases, sales, and all of the information around the graph. But it really falls down to these core components. You've got relationships, you've got entities, and you've got descriptions about those relationships. It can even be more simple than that. It doesn't always have to include each of those items, but it typically does these days with the graphs that I'm seeing organizations create. And so because graph analytics is really firmly rooted in graph theory principles, I'm just going to talk about it briefly. I'm not going to really dive too deep into it. But graph analytics, the graph representation, when you see it in equations, it's formally represented by G equals parentheses V comma E, where V is going to be the vertices or nodes, and E is going to be the edges or relationships. The vertex set of V represents the entities in our system, so people, products, events. The edge set, E, represents all the connections between them in our graph, and the properties are those details which we talked about. So ways that we can use that really are paths and connectivity, understanding how nodes are connected, centrality measures, identifying the most important or influential nodes in that network, community structure, discovering groups or densely connected nodes, network flows, analyzing the movement and capacity within the network, and graph algorithms, which apply, there's lots of different types of algorithms, but you can apply these algorithms to solve specific problems, like finding the shortest paths or identifying patterns within the network. And there's a lot of advantages to graph analytics: natural data representation, performance in certain circumstances, flexibility. It really does very well for pattern detection. So it can identify common substructures or recurring patterns within your graph. Think about the complex graph. I love using Facebook because they, in my opinion, were one of the best implementations of graph theory. So think about all the patterns there. that you could visualize or that could arise. Doing traditional analytics, what a nightmare. I don't even know how you would do that. Maybe you use some machine learning, some clustering to try to identify groups and common characteristics, but to really see the graph and identify the relationships between them, that's really where graph analytics comes in. So you can discover similar subgraphs. So thinking about that example of Facebook as big, if they're visualizing like all the active members of Facebook, there should be subgraphs in there. And there could be similar patterns within different customers in these subgraphs with different purchasing patterns, different relationships, different influential people, and they're able to break those down. You can track temporal patterns, so analyzing how graphs change over time. One of the most common uses really is path analysis, connecting a path, finding like the shortest path between two nodes. You can do route optimization, which is determining the best path for like delivery and logistics in supply chain. Dependency analysis, understanding the dependencies between tasks or processes. That's one that I don't see as often. I'm sure it's out there, but understanding the dependencies, I haven't personally built one of those, but I can imagine how that could be insanely helpful. And flow optimization. This is incredibly important for supply chain, optimizing the flow of goods, information, or resources within the network. And community detection, that's a hugely important use case of graph analytics. So community detection is like group discovery. So you can identify groups of closely connected individuals or entities. Think of those nodes. Cluster analysis, grouping similar nodes based on their connections and properties. Social network analysis, understanding social structures and relationship. Segmentation, you can divide that network into meaningful segments. Maybe you use that for targeted marketing. Very helpful. And you'll see some overlap like, oh, this sounds like some things I could do in machine learning. Yep, you sure could. But the benefit is of graph, using graph analytics, if you're using a graph database, is that speed, being able to navigate these relationships and that network very efficiently. So the business value proposition of graph is really being able to take these complex networks, uncover hidden patterns, try to do real-time graphs, being very efficient for better customer understanding, fraud detection, risk assessment. There's just so many awesome use cases, which we'll talk about with graphs. And so the current state of graph analytics, it's experiencing, as I noted earlier, rapid growth across lots of different industries. It's been in finance and healthcare for a while, social media, e-commerce, but the technology stack is definitely maturing. There's very robust graph databases, powerful query languages, and very sophisticated visualization tools out there, open source and proprietary. So I think those things really had to come together in order to fuel that growth. Before, it used to be very, very difficult to build a graph network, and graph database technology was fairly limited. But given the rise in interest, there's been so many more advances in all parts of the graph analytics process. And the scale of the graphs also are increasing. So if you think about the amount of data that we have, and it's just growing with the Internet of Things, we're connecting so much sensor data, we're connecting data on everything. We're connecting data on my fridge. We're connecting data on key card swipes. And we have all this data that in a traditional manner would be incredibly difficult to analyze or resource intensive, where there are use cases where graph analytics is really going to come in and just be much more efficient and powerful. And as a result of that, we're able to build much bigger networks, billions of nodes and relationships. So it's just an exciting time to talk about graph analytics. Everything's moving fast. It's allowing organizations to respond to events and changes as they happen. And I didn't put it in the slide here, but I do want to mention just like the 4 V's of graph data. I feel like if I'm going to talk about the fundamentals, this is something I have to talk about. So the 4 V's of graph data, when you're looking for like what kind of data would be appropriate for building out a graph network. The first is volume. So I love that they're all V's, and I didn't invent this. This is a thing before me. So the first is volume. So the volume of data you want to consider. So if you have billions of nodes, but you don't want to pay to analyze billions of nodes, you need to consider that. So you want to be able to understand what the volume is of the graph data that you want to analyze, the velocity, how fast is it coming in, and do you have the systems to support real-time analysis, or do you need to do batch? The variety, what types of nodes do you have? Are there many, many different types of entities? Because that'll determine the relationships between them. And the valence. So the valence refers to the connectivity between patterns in the graph. So is the relationship really dense, or are there only a few connections between the nodes? These are all things to consider when you're starting to think about, is my data appropriate for graph modeling? And so we talked about some of the common graph techniques. I want to bring up some examples. So some of the most common, these are the three most common, and then we'll talk about the network metrics. So we've got path analysis, or the distance between nodes, and there's different ways to do that, community detection, and then centrality analysis. And we'll look at each one of those in addition to the network metrics. And so path analysis really is, and I want to make sure I'm running out of time. I'm just too excited about this. I think I'm going to run out of time. So I'm going to speed it up a little bit. So this is really, path analysis is really like transversal. Like, how can you get in between each one of these, between these two nodes? So there's lots of different algorithms that you can use there. Think about like Google Maps. That's a version of path analysis, finding the shortest route within certain parameters. You've got community detection, which, as we noted, and there's so many different methods around community detection. There's the Louvain method, which is, in my opinion, the most widely used of the algorithms for community detection. It's really great with large networks. So Twitter, for example, uses a modified version of Louvain to identify topic communities and improve content recommendations. Netflix uses a version of Louvain for label propagation. It's simpler than Louvain, but it's highly scalable. There's K-core decomposition. So there's lots of different algorithms and applications in each of these overarching applications. And then centrality analysis. So centrality analysis is really interesting. It can help with understanding influence, and there's different ways to look at it, but there's like degree centrality. So examining the core measures of density, like where is a lot of the relationship landing? So it can help you identify like influencers. There's much more sophisticated insights that you can gain. You can do betweenness, centrality. A little more sophisticated. It measures how often a node lies on the shortest path between nodes. JP Morgan Chase uses betweenness centrality in their risk analysis to identify critical financial institutions that could pose systemic threats to the market. There's eigenvector centrality. And eigenvector centrality measures influence by considering like not just how many connections a node has, but how important those connections are. And like Google PageRank, the Google PageRank algorithm, that's a variant of eigenvector centrality. There's closeness centrality. There's a few others. And then the network metrics. So there's some core network metrics that we can look at. But I don't want to run out of time before I just show you a quick demo, but just some best practices as you think about building out graph networks. So you want to optimize for specific analytical goals. When you think about, well, you just covered a million things. There's so many different techniques. What should I do? Where do I start? Start with a use case, a specific goal, a specific network, and that will guide the techniques that you use. Like, how big is the network? How complex it is? What kind of insights do you want to get out from this network? What's going to drive business value? That's where you start. And then you build the process around that. And you do want to prioritize performance and scalability, maybe not in your POC, your proof of concept, but that's just get it out the door and see, does it work? But as you start to scale that, you really do want to prioritize performance and scalability, because the data can grow very quickly and you want to make sure that you can keep up with that. And there are some modeling pitfalls that I'll cover. But as I noted, the tool ecosystem, this is only like 1/100th of it. The tool ecosystem is just growing like crazy. You've got Neo4j, which I recommend checking out. They have some really great, in the box sample graph data sets that you can play with. It's kind of drag and drop. You can do it in Python, which I prefer to do. There's so many. I'm going to show NetworkX, that package in Python, but there's so many other packages you can do. There's so many. And then the physical graph databases, there's Tiger Graph, Amazon Neptune, Neo4j, as I noted. Like there's so many, and there's more coming every day. So I encourage you to explore, like, what are all the different tools out there that can help me do graph analytics? Because you can do it completely open source, which I love. Or you can, you can modularize it and say, okay, well, I'm going to do this part open source, and I'm going to pick this proprietary tool for this aspect of it, or mix and match, which I love. Gives you a lot of flexibility there. So I want to dive in and just show you how simple this can be, just give you a taste of what graph analytics can look like. So this is super simple, but it's just in Python, using that NetworkX package, matplotlib, numpy, and then the community. So I'm going to just briefly walk through the code and just tell you what it's doing, and then I'll run it and show you what the output looks like. So I'm just having it create its own connected graph. I didn't go create I didn't pull from a graph database. I thought about pulling one from Neo4j, but I figured I'd just keep this demo super simple. So this is saying, hey, build a connected network with 25 nodes, add some weights. We didn't talk about weights, but that can be relationships, can have different weights. Not only direction, but also weights on them. So I do want to add weights in there between 1 and 10, and it can randomize those. I want it to do shortest path analysis. I'm going to have it also give me all the different paths available between the nodes. I'm going to have it explain it to me, so giving me the outputs. I want to do weighted path, because remember, the shortest path and the weighted path could be different. So the distance between two nodes could be one thing, but once you add weights, maybe I want the lowest weight distance between the nodes. So we're going to do that. We're going to output that. We're also going to do some community analysis. So we'll do some centrality analysis, and I want to look at a few different versions of it. So we'll do degree centrality, betweenness centrality, closeness centrality, and eigenvector centrality. Visualize that. I'm running out of time. That's why I'm trying to fly through this for you. And then network analysis, getting a good idea of what does that network look like. Show me the shortest path within the network, and let's visualize it. I'm going to do a few different algorithms there. So, I mean, you can see, I just talked through that, but that's right there. That's all just Python. So had I connected a real data set to it, it would be the same Python. I just would have connected it to a graph data set. Okay, so it already ran. So here's just some of the output we'll talk through quickly. So we've got shortest path, number of hops, 1, but the weighted path, it gives me the weight of 3. So you can think about different use cases where you want to think about the weight of the relationship versus just the number of jumps between two nodes. It gives me all the, it's going to give me an error here saying I'm using deprecated code. I know. I should have gone in and updated it. So some examples that I thought of were, so for like shortest path, network, transportation network, like what's the fewest stops with the weighted path? Like what's the most efficient route? If you think about fuel, if you're thinking about like maybe there's each street has miles per hour, you want to consider that with your route. If you look at a computer network, minimum hop routing, you can read. I don't have to read this to you, but there's lots and lots of different applications. So here's my network graph of 25 different nodes with all their different weights. So shortest path between 0 and 24, those are the two nodes that I told it to find. It's 1 hop, and here the weight is 3. So it was still just 1 hop in this instance. If 24 was over here, it could have been longer. Looking at centrality analysis, yes, it gives us the output, but we can also see the graphs. So we can look at degree centrality. So how many relationships does it have? So I had it put out blue, and the more dense the degree centrality is, the darker the node is. The betweenness, how often is this on the shortest path? Closeness, eigenvector. So it gives me a good, just running, see, I just ran all of those centrality analysis in one. So then I can look at it and get a good feel for, oh, okay, what's the sense of my graph? And depending on the use case, I would probably pick one specifically, but this is just an easy way to view all 4 of those different techniques. And then network analysis. And so there are a few different ways you can use network analysis, but I like to look at, so like interpretation, the network diameter is really like how far the two most distant nodes are. We can look at average shortest path, network density, which is an important one, which is the proportion of possible edges that are present. So the more dense means more interconnected the network is. So here's an example of what that network structure would look like to help you see like what's the betweenness of the centrality nodes. And then looking at community. So I had it color code the different communities by color. You can do it in different shapes. I chose to do a circle because that helps me visualize it sometimes not, depending on the data set. And yes, I know I need to update my code. And then community with boundaries didn't work great on this one, but you can have it draw the boundaries instead of color coding. You can have it draw specific boundaries between groups to help you really visualize exactly what you're looking at. And so just quickly, I know I'm at time, but something that's come up a lot and that I'm researching and writing about a lot recently is graph RAG. So in Gen AI, we're using RAG a ton, and graph is, as you can see, combining them together is amazing. So vector databases are really what's fueling RAG. RAG is the retrieval augmented generation. So it's pulling from a knowledge base. It's pulling from a knowledge base, but combining that with graph explains the relationships between these entities. So if you can have the relationships and the knowledge base together to fuel your generative AI, it's going to make it much more powerful. And so a lot of companies are seeing that graph RAG is a very good way to build like agentic AI, for instance, that very specific use. Understanding those relationships and the surrounding knowledge context will be just pivotal for RAG. If you're not building a foundation model, which is like the big I can do anything model, if you're building the small language model or agentic AI, this is incredible. That's my time. Thank you so much for letting me come and talk about graph. I hope we can connect on LinkedIn and talk more about it, because it's an incredible technology. You can do it fully open source. And thank you again. I've really enjoyed being here.